Thank you. Pleasure to be here. Thank you, David. And Stephen. Okay. So I'll be talking about the Schensted Knuth correspondence as a linear operator. And to explain, let me just give you a small example of theory. Such that it is. And so this is just for this is going to be, I'm going to define a ring Rmn. It's just going to be the polynomial ring in this case, 4 variables. So this is m equals n equals 2. So usually RSK is a set bijection between matrices with non-negative integer entries and pairs of semi-standard Yong tableaux. And just to show you 2 examples. So here, of course, this could be matrices with any sort of non-negative entries, but I want to only talk about permutations for the moment. So example number 1 would be alpha is just the identity permutation. And this maps under RSK to a horizontal domino. On the other hand, I could have the other permutation S2. And this maps to the vertical domino. So in order to turn, I want to turn this set bijection into a operator on Rmn. And what you do is, I'm just going to think of this matrix as an exponent matrix. So Z alpha is going to be Z to the this matrix, and that's just going to be according to the coordinates C11, C22. Over here, same thing. C12, C21. Now I'm going to define for you the operator in this example. I'll call it T just to differentiate it from RSK. I'm going to define this to be C11, C22, but here it's actually a product. And you should think of this as a product of 1 by 1 minors. 1 determined for every column of the shape. And the fact that there's a 1, 1 here is because there's a first row, first column, second row, second column. So these are 2 1 by 1 minors. Over here, the definition of T will send this to a determinant. And this is 1 determinant because there's 1 column, first and second row, first and second column, so it's that determinant. Does that make sense? Definition, at least in this case, makes sense. So I'm defining those to be what the map will send it to, and then of course I extend linearly. Let me let R be the span of C11, C22, and the other monomial. By our definition, P sends R to R. And we can write down the matrix of T, change of basis, basically. Well, it's going to be this matrix. And the way I'm doing it is I'm ordering the basis like that. So according to our operator, this monomial gets sent to itself, so therefore you get 1, 0, and the other monomial gets sent to the determinant, which is the difference. Therefore you get 1 minus 1. And it is this object that I want to study during this talk. Okay. Now I want to explain where these determinants, how they lie in the literature. This is topic of standard by tableau. I guess versus monomials. So in general, I'm looking at the polynomials in m times n variables. So the coordinate ring of matrices. And it's just a polynomial ring. So let's ask what bases there are. There's the monomial basis. So pick your favorite non-negative integer matrix, alpha, and then just associate it to the monomial, just as we did over there. Second one is the standard by tableau basis. And I will just give you a notation at the moment. I have 2 semi-standard Young tableaux of shape lambda. And this is going to correspond to a product of determinants, 1 for each column. And P tells you the rows of the determinant. And Q is giving you the column indices of the determinant. But once again, in our 2x2 example, you have this is your P and Q, and this is telling you first row, first column, second row, second column. Same thing over here. Is the definition of square bracket PQ understandable? Okay, good. This must be very classical, but the fact that it's a basis is a theorem due to Dubélé, Rota, and Stein in the 70s. They give a straightening algorithm, and this is what proves the basis of RMN. Okay. RMN's polynomial ring in the many matrix number of variables. It's graded by degree. So this is going to be the span of the degree D monomials. In other words, where alpha is a matrix whose total sum is D. And we're not going to go through the algorithm of RSK, but the basic, textbook discussion will show that in this language, oh, sorry. I should explain the definition. The definition in general is due to Brunson-Hanka. It's going to be a map T from RMN, and it's just going to send alpha, C alpha, to the bi-tableau P alpha, Q alpha. So in words, if you understand RSK, you're going to get a parent tableau. The parent tableau turns into a product of determinants. and the map is just going to send the monomial, in other words, the matrix, to its corresponding tableau, and extend linearly. So what I want to say here is that this is an operator on infinite dimensional space. Let's just do one step and turn it into a matrix. Here you have the span degree D monomials. And it's easy to see that T restricts to any of these five-dimensional subspaces. Because all I'm saying here is that if a matrix has total sum D, each of the tableaux that appears has D entries by how RSK operates. Now, as a matrix, there isn't any mystery. The beta alpha entry of the matrix of T is just the coefficient of the monomial C to the beta in this bitableau. So in other words, in order to calculate any particular entry, just as we did in our basic example, you're just expanding out determinants and multiplying them out and foiling and collecting a coefficient. Okay, there can be signs, of course, because it's a determinant, but in principle, there's no big mystery. However, what Bruns and Konka asked in the early 2000s is to understand some insight about the linear algebra of T. And the goal of this talk is to provide a first systematic approach to their question. And we'll do it in terms of what I'll call a block decomposition theorem. And this will lead to some results and statements about diagonalizability of T, the determinant, the trace, and something about the eigenvalues. And implicitly something about the eigenvectors. Any questions so far? Yes.
Yeah, I think you could probably also fix the row sums and the column sums.
We'll do in a moment.
Okay.
Exactly. Yes, you foretold my next step. Okay, let's follow Stephen's recommendation. Okay, so what Stephen is saying is let's refine further. And and this is what I'll call weight spaces. So what Stephen is saying is let's think about a matrix alpha. Again, non-negative entries. And then I'm going to impose that the row sums are fixed. And then you also have column sums fixed. So you're asking for all matrices with these rows and column sums, like a transportation polytope type thing, right? That have this property. So I'll just denote that by row of alpha is sigma and column of alpha is pi. The collection of all such matrices I will denote by this symbol. So really it depends on M and N, I guess, as well. These are contingency tables, if you want to look them up. Okay, so with that, let me define another subspace that depends on input of sigma and pi as well. It is just going to be the span of all C alphas where alpha is a contingency table. Now, if you have a matrix which satisfies properties, then evidently the sum of the sigmas equals the sum of the pi's, and then some number, let's call it D. And so therefore, this is a subspace of RMN D, where D is that. Any questions? Okay. It is also true that the T operator, the RSK operator, fixes Mn sigma pi. This is also pretty clear from the definition of RSK. Or at least you can check it in one example.
Is the dimension of Rm and sigma pi something symbol?
No, to follow on Colleen's conversation, this is sharp P complete in the inputs of sigma and pi in binary. So in fact, knowing the dimension of this matrix is if you could solve it, then P equals NP. But that's not my concern. I'm just interested in thinking about this matrix anyway. Still talk about it. Okay, what can we say? Okay, so first principles is the T. Let me now use a little bit of extra notation just because we have a lot of different versions of the operator flying around. I'm fixing Mn and D. Since it's fixing all these weight spaces, it's going to be a block decomposition over all these smaller matrices. So block decomposition, but not the one I want. This is sort of, I'll call this naive block decomposition. The question is, when are two blocks similar? Because we want to reduce this block decomposition as much as possible. So when is this thing similar to M bar, N bar, sigma bar, I bar? So I'm even thinking going across different sizes of matrices. So of course, if they are similar, the trace, their eigenvalues, diagonalizability is the same. Okay, there's an easy but useful case. That's if sigma bar is sigma with a zero added or removed. Or similarly, pi is pi with zero added or removed. So all I'm saying here is that if I have a matrix, I don't know, 2, 2, 2, 1, 1, with these conditions, these row and column conditions, that if I stick a zero somewhere, then it doesn't act like that. It doesn't change anything. Like the bases, of course, will be in bijection because the rows here are forced to be zero, those columns are forced to be zero. So nothing is going on up to just a dumb shift. So that's an easy case, but it'll be useful for us because now that means that without loss of generality, I'm going to assume sigma and pi have no zeros. It's just notationally more convenient. So if I'm in this case, I might as well talk about that case. And so therefore, I can now talk a little bit more handily about just the operator sigma pi under that hypothesis. Any questions?
So the M and N are sort of going away because M is just the length of sigma, N is just the length of pi.
Correct. Exactly. Okay, so this brings us to our, I think, fourth topic. Correct. This is our main source. So I'm looking for similarities to use, and our main source comes from the following. I want to think about, let's fix K and L.
Can I ask a different question? Sorry. Earlier when you were writing this, you said, oh, this is a block decomposition, but not the one that we want. This is a naive one.
Yes.
Can you say a little more about why this one is not the one you want? Maybe I missed it and
Well, let me show you the results of
Okay.
the non-naive one, and then you can decide.
Okay. So in other words, there's a better one, is what you're saying, and I don't know.
That is my
Okay.
thesis.
Okay.
But yeah, it stands to questioning. Correct. Okay, so towards this other block decomposition that I want to talk about, the scare quote one, I'm going to fix K and L, and I'm just going to talk about another linear operator, psi, and it's going to go from degree D to degree D plus 1. And all it does is it takes a polynomial here and maps it to the polynomial times the variable, CKL. Here's the theorem with Ada. This map, you restrict it to sigma and pi, will of course go to sigma plus ek, the standard basis vector, because you're shifting degree, the kth row, and then the kth help column is a linear isomorphism. And moreover, not only is it linear isomorphism, but it's RSK commuting. The words don't do a whole lot of good, but I just want to use them a little later for shorthand. RSK commuting just means that it commutes with the RSK map. What do I mean? I mean that T sigma pi, if you then pose it with KL, this is equal to precomposing E. So in other words, if this is indeed an isomorphism, this is a similarity of matrices. So this will be our main source, but it's not true always. It's true if and only if sigma k plus pi L is greater than or equal to D. That's the condition. In fact, let me just pause to remark that if this statement was true without the orange condition, then that would be equivalent to saying that the RSK is actually an algebra map. But it's not an algebra map. It sort of behaves like one in certain root directions. Let me say a word about what that orange condition is actually saying.
That's a question.
Yes.
In the theorem, the similar matrices, are they acting on the same dimensional? Like, are they matrices of the same size?
Yes, because I'm assuming that sigma and pi have no zeros. So you're just shifting in one position. This is part of the hypothesis that because of the easy case, I might as well assume without loss of generality from here on in that sigma pi have no zeros.
Well, I understand the alphas, but the t's themselves, they act on like the monomials, right? So
That's right. So there's an isomorphism of these vector spaces.
okay.
That's the assertion. It's the linear isomorphism.
Ah. Okay.
Exactly. Good question. Other questions? Okay, so I want to just say a word about what this is actually saying. So maybe by example is easiest. So this is my sigma and my pi over here. And we look at this condition, right? And the total D here is equal to 4. Any matrix satisfying these conditions has total sum 4. And you'll notice that according to the condition, I'm allowed to use this position or this position. These are two places where sigma k plus sigma L is greater than or equal to 4. In other words, 2 plus 2 equals, well, greater than or equal to 4. And 2 plus 2 is greater than or equal to 4. So let me choose k equals 2 and L equals 1. So what we're doing when we add those standard basis vectors is we upgrade 2 to 3 here, and we upgrade 2 to 3 there. So now the sum of these two things is greater than D. So what is that saying? If I look at this row, it has sum 3. And if I look at this column, it has sum 3. The question is, right here, does that have to be non-zero? And it does by the pigeonhole principle. So what this means is that this condition exactly says that in the target space, you are forced to have a variable there. So by that pigeonhole principle argument, that easy pigeonhole principle argument, you have divisibility there. Well, the psi map is always injective because what it's doing is it's taking any monomial, basis of monomials, and sending it to another basis by multiplying by a variable. That's obviously an injective map. How could you fail to be surjective? You could fail to be surjective if there was something in the target that didn't involve CKL. You would never be able to hit it. But this pigeonhole argument says you do hit it. So that's the content of linear isomorphism. The statement that it's RSK commuting, i.e. it satisfies this condition is harder. And to prove it, you need to actually delve in, well, we need to delve into the actual combinatorics of RSK. So I won't do that here. Questions? So the name of the game is reduction. If I have some sort of pair sigma pi like this, I look for the position K and L, which is greater than D, and I just reduce to the smaller case over here. Right? And I obviously, just because I like to, I want to make the numbers as small as possible. And when you fail to make it to do that, you fail exactly here, because here actually pigeonhole doesn't tell you anything. So it's really that threshold case of pigeonhole. That motivates the following definition. I want to define sigma and pi, a pair, to be reduced if you can't do that. In other words, maximum of K plus the maximum of over L is less than equal to D. So exactly in this example over here, satisfying 2 plus 2 equals 4. This is logically equivalent to the following statement. Let me take the greatest common divisor of all monomials in that space. And it's 1. When you reduce, you have no common variables among all of the monomials. That's an equivalent statement to this. So in that sense, R sigma pi reduced has a primitivity to it. It really is saying that you're co-prime among the monomials. So therefore, you can play this following game. If you give me your favorite sigma and pi, I can keep on playing this reduction game until I get to some reduced case. And so now we're going to try to address Martha's question, which is the block composition.
So is it always unique, the reduced?
Yes. Because like basically, if you give me sigma pi, just look at the greatest common divisor. You just divide that out. There's no confluence type well-defined as questions. Okay, block decomposition. So reminder, we had that T is equal to the, actually, let me write this. Okay, so we had the decomposition, the actual block decomposition into pieces. And this is over all possible pair sigma and pi. But now we know that many of these are similar by this reduction. So therefore, this is going to be similar to another block decomposition over sigma and pi reduced. Take sigma pi. And many blocks that are the same can occur. So there's multiplicity. So this statement has no content so far. You just reduce by definition, and then of course you can make the you can collect terms. The theorem here that we use is that in fact this multiplicity is quite simple. It is not of the order of complexity of in Colleen's talks. Is explicit. And when I say explicit, I mean essentially it is a product of three binomial coefficients. That says stars and bars. Okay, composition problem. Okay, why? Remember that, like, let's suppose I have this reduced pair here, sigma and pi, and I want to boost it to being something that lives inside a 3 by, I guess, 6 matrix. Well, what I can do is I can just put in zeros in appropriate places, right? We said that's absolutely innocuous a move. And so how many ways are there? There's gonna be 3 choose 2 ways to do it this way, and 6 choose 3 ways to do it that way. And so that accounts for the binomial coefficient, this and this. And then finally, once you've placed it, really what you're asking is, here's a degree 4 thing. Let's say I want to add a degree 40 thing. The places where I can apply the variable multiplication theorem are in this pink and orange spot. In general, maybe there are 5 spots. So you're asking how many ways can you put 36 things into 5 slots? In all possible ways. That's stars and bars. I only say essentially because there's some annoying bookkeeping which doesn't make this literally true, but this is the truth. All right, now I want to talk about consequences of this formula. So first of all, let's talk about the determinant and the trace. When you have some block decomposition, as I'm sure you're well aware, the trace of this is going to be the sum of the traces of these, and then really with a multiplicity. So let's fix D, fix the degree. Then the first statement is that the trace is a polynomial in M and N. This is basically immediate from this formula. There's your M and N. When you fix D, there's only so many choices here, and so it's a polynomial in that way. The stars and bars won't involve M and N. That's the proof. We could say a little bit more. The little bit more is that the lead term is the trace of case 1 to the D, 1 to the D over D factorial squared M to the D, N to the D. Okay. I should put quotation marks for one moment. So what I'm really saying is in our first example, that was the case D equals 2, permutation matrices. So I'm looking at just Schensted in that case and analyzing that operator. And that controls the leading term of this polynomial. I would like to say it is just simply the lead term, and therefore the degree is simply 2D. But I cannot, because here, in the case D equals 2, the trace is 0. Remember? The matrix is 1, negative 1, 1, trace is 0. But actually, computationally, that's the only case where it's 0. I believe that it's always non-zero. Otherwise, in fact, I believe it's going to infinity from all I can see, but I cannot prove it. So we conjecture that this, the degree is 2 to the D, 2 times D. The other statement is that, again, fixing D, I want to talk about the determinant. First of all, it's easy from first principles to see that the determinant is always plus or minus 1. Why? Because it's an integer matrix, it's invertible, So if they have any determinant, they have to divide 1. That's not the content. The content is this is periodic in M and N. More precisely, let me pick R such that 2 to the R is greater than D. Then I'm saying that the determinant of the trace of M, N, and D is the same thing as the determinant of the trace of M plus 2R, N, and D. This is an easy consequence of the block composition theorem because the formula involves binomial coefficients. So I'm just applying Lucas's theorem of binomial coefficients. I do not know the exact periodicity. So this is guaranteed to be true, but it could be smaller.
Yes. The determinant of the trace.
Did I say trace? That's thank you. Thank you. Good. Yes. Questions? Other questions? Okay, let me go on to diagonalizability. So I'm going to give 2 versions of the statement, one of which was due to us and one which was reformulated due to Fomin, and you can tell me which one you prefer, but I'll start with ours because I want to at least show what we did in comparison. Okay, so the statement is that T, M, and D is diagonalizable if and only if one of the following is true. Either M, let me first, just for simplicity, let me assume M is less equal to N. By transposition, this is not an assumption. So I either have M equals 1. In that case, the matrix is just the identity matrix. So that's clearly diagonalizable. You have low degree cases. D is at most 3. You have M, N is equal to 2, 2, and D is whatever you want. Or M, N equals 2, 3, and D is less than or equal to 6. That was our theorem, our corollary. So now let me show you an equivalent formulation. So maybe it's easier to do it by a picture. Let's look at this example here. 2, 3, and let me just choose equal to 5. So what I'll do is I will have a central vertex, and this 2 will correspond to a path of length 2. This N is going to be a path of length 3. And they're going to overlap at the central vertex. And finally, the 5 is going to correspond to a path of length 5, again overlapping at the central vertex. So this is It's E8 in the Dynkin diagram classification. And the statement, the reformulation is that you are diagonalizable if and only if D is less than 3, or you are one of the ADE Dynkin diagrams, or E9. E9 would be the one that corresponds to adding another node. We do not know any sort of reason for this other than the computation. What the block decomposition theorem does is it allows you to cut off many cases by looking at the smaller blocks and show they are not diagonalizable. That non-diagonalizability propagates because of the embedding that we are doing. And that just cuts you down to a small number of cases, shown by a version of the theorem, and then we just check in those cases you are in fact diagonalizable. The final topic is following corollary. This has to do with, I'll call it Galois complexity. So not P versus NP complexity, just Galois theoretic. What about the eigenvalues? How complicated are they? Statement is that if M is greater than equal to 3, N is greater than 3, and D is greater than equal to 4, then the following is true. Let's look at the characteristic polynomial of our matrix. That is to say, the determinant this thing has an irreducible factor whose Galois group is S5. I'll call this irreducible factor H. So Galois group is going to be, you take a splitting field, you look at automorphisms that fix the base to the cube. This is isomorphic to S5. And therefore, by Galois theorem, you have unsolvability of the roots. So therefore, we cannot expect a simple formula for the eigenvalues. In contrast, in particular, with this ADE situation. If you're thinking Coxeter theoretically, you're thinking the eigenvalues be cyclotomic in some way. Absolutely not true. I just have one last question, or maybe I want to ask. Okay, we showed that S5 appears. What other Galois groups can appear? So actually what we did is we took sigma equal to 2, 1, 1 and pi equal to 1, 2, 1. Just that example. This thing has a factor with the Galois group that is S5. So this has an irreducible factor, I'll call H sigma pi, and then the Galois group of this is S5. And because of the decomposition theorem that allows you to propagate to show this for all greater than or equal to 3 and greater than 3 and D greater than 4, the 4 is because 2 plus 1 plus 1 equals 4. Question is, what Galois groups can appear in this way? By which I mean, for these particular blocks, what sort of Galois groups can appear, right? And one of the things that we can show is that all of the group of units appear. And the conjecture is that in fact all SR appear. If this were true, then that would mean that this problem genuinely has very high Galois complexity. Every possible generic Galois group can appear for some irreducible factor. Thank you.
Are there any questions?
So RMN is, I would interpret that as like a coordinate ring. Is there a quantum version of this story where T is mapping between quantum groups?
I believe that there is such a story. I'm just trying to recall the authors at the moment. I don't know how to make that work, though. But you might.
Can you get any similarity by permuting the entries of sigma or pi?
No, actually, it's actually so. Right. What is quite stunning is that all normal things you would do with these tables, if you interchange the rows, the row margins, then you get a new equinumerous count. Because nothing's really happening. But you can show by a simple example that you actually get not even similarity. Not by RSK, but just purely not, like different eigenvalues, etc. Are all the conditions here?
Like, so n equals 1 or t less than.
Yes, yes. These are all ors.
So what are the implications of, you know some structure of this operator T, and you presumably want to learn something about RSK. Using these properties, can you give an example?
It's a transition matrix. So Koska coefficients are transition matrix. Casuistic polynomials are transition matrix. Character tables are transition matrix. So frankly, we're just trying to do it for fun.
Fair. That's very
Yeah. So the one definition of the Specht modules is taking similar determinants from a tableau and like symmetric group back. Like, does this tell you anything about the representation theory of symmetric group?
Not that I know of.
If there are no questions, let us thank Alex again.